magnetic field of the curved analyzer magnet, where the arsenic ions are isolated. Because this is a shallow implant, the pure arsenic beam does not need to be accelerated. A selectable resolving aperture removes contaminants whose atomic weights are so similar they were not distinguished by the analyzer magnet. Different sized apertures are used for different dopants. When ready, the flag Faraday moves out of the beam's path and allows the implant to occur. This controlled implant creates a gradient as a low concentration of arsenic ions bombard the areas beside the gate. Photolithography now uncovers the P-channel transistor. As with the N-channel transistor, a halo implant occurs using antimony, an N-type material. The low-energy, high-current implanter then uses boron to create the lightly doped source and drain regions of the P-channel transistor. This provides a gradient between the edge of the channel region and the heavily doped drain. A silicon dioxide layer is deposited and then etched vertically. This creates oxide spacers along the gate sidewalls. Both N and P-channel transistors undergo implantation again with high concentrations of dopants. Arsenic is used for the NMOS transistor, while boron is used for the PMOS transistor. The result is a source and drain with heavily doped regions and a lightly doped area protected by the spacers. This increases the reliability by spreading the voltage drop near the drain. The halo implants allow the short transistors to behave like long ones. All the implants for the source and drain are now in place. To activate these dopants, the wafers undergo annealing at high temperatures using a rapid thermal process. Rapid thermal annealing can be done using light, such as tungsten lamps, or heat, as with this rapid thermal furnace. This RTP system anneals one wafer at a time. It contains 2 silicon carbide bell jar furnaces with 3 different heating zones. From underneath the furnace, the elevator moves up to preheat the quartz tube. Inside the furnace, a wafer is placed on quartz pins mounted on a quartz ring. A pyrometer head focuses straight up the elevator tube to measure the temperature of the back of the silicon wafer. Then it does one pre-sweep to check the reflectivity of the wafer while it is still cool. Once the wafer measures 800 degrees, it is elevated to the top. The wafer stays in that region for only 1 to 2 minutes at about 1000 degrees. This reestablishes damaged bonds and activates dopant ions. In a typical batch furnace, this process requires 20 to 30 minutes at high temperature. Because this heat also affects the location of previous implants, single wafer rapid thermal heating is the preferred method for activation and annealing. The electrical characteristics of the substrate are now changed, and ion implantation is complete. The wafers will now go on to the next stages of fabrication, which include building the intricate wiring needed to connect the millions of transistors found on a single chip.